I think we've got a student. We've got Phoebe. We've got Phoebe. Who else?
Hi, I'm driving again.
Hello. Let's see who
I'm
else.
driving.
Oh, you be careful. I don't want you getting hurt.
Okay,
Now there's Christy too.
alrighty.
Christy's on board. And Phoebe, you can always watch the YouTube when my daughter puts it on YouTube. So that's okay too. But right now, all we got is Phoebe and Christy. And we'll wait a minute. Oh, there's Daniel. We'll see who shows up here. We just have the three of you. You've got 2 minutes before class starts. Did you have any questions for me, anyone? Well, let me tell you how you did on that test. I'll give them back to you Thursday night. But here's how the class did. Well, that's how the class did. The average was 76. So it was a fair test. I didn't make it too hard or too easy. And some of you did quite well. Those of you that didn't do so well, do not despair. You can still get a C in the class, but you're going to have to do better. You can't keep doing 55s or 54s. If you keep doing that, something bad's going to happen. So you've got to do better. I put the key on Blackboard. Let's see who we've got now. Well, just the three of us. Phoebe, Daniel, and Christy is all we got right now. But the key is on Blackboard. So you can pull that up, and when you get your test Thursday night, go over it, make sure that I didn't cheat you. Now, if I cheated you, I'll make it right. If I made a mistake, if I forgot to add a page or whatever, I'll be glad for you to have more points. I can tell you how many points were on each problem. The problem 1 and problem 2 were 20 points. That when you look at your paper Thursday night. Problem 3 was 18 points. Problem 4 was 18 points. And problem 5 was 24 points. I was fairly pleased with your problem 5, that Kirchhoff voltage law. A lot of you got that. I was proud of it. Well, let's see if anybody else has showed up yet. I might just be the 4 of us. No, we got Daniel now, and Nicholas. Nicholas, Christy, Daniel, and Phoebe. And we're going to start our class now, unless you have a comment or question. Go ahead. Okay, well, let's start our class now. That's how you did on your test. There was 1A, 3 Bs, 4 Cs, and we won't talk about these, but we're gonna do better. And you can double up the final. If you'll read the syllabus, I'll double the final. And so you could replace that low grade with the final score, which would maybe help you out a little. Now, this course has 2 parts. Physics 2 is broken into 2 parts. The first part is electricity, and we just completed that. And tonight we start on magnetism. We've studied electricity up until now, and now we're going to study magnetism. And this starts with chapter 11. See, electricity, I think, started with chapter 5, I believe, wasn't it? Yeah. It was chapter 5, 6, 7, 8, 9, and 10. Holy cow. All those? Have we done all those already? I'm afraid so. Gosh, the semester, I guess, is maybe half over, you think? Well, anyway, we're going to start on magnetism now. That's the second big part of this course. I'm going to go back to this chapter 11 here at the beginning and see what they say about magnetism. You've all probably played with magnets when you were a kid. I'm looking to see if they have the Ørsted, if they talk about Ørsted's experiment. Let me look in the index here. I don't see it there. I tried to find it. There was a guy named Hans Christian Ørsted. Yeah, on page 499, it tells about his experiment. In 499, on page 499, he had an experiment. This was in 1819. Gosh, long time ago. What is that? That's 201 years ago, right? Yeah, this is 2020. So that would be 201 years ago, the Danish physicist, he's from Denmark, Hans Ørsted, discovered a connection between these two. Up until then, people thought they were completely separate. They knew about them. They knew about magnets. And they knew about electricity. See, lightning would strike a tree and the tree would burn. They knew that was electricity. And, well, the Chinese discovered the compass, which works on magnetism. And with that compass, they were able to sail out into the ocean beyond the side of land. So they knew about both of those, but they didn't know the connection. And on page 499, it talks about a guy named Hans Ørsted. Is that how you spell it? Let me see. Yeah. Wait a minute. There's no A in it. It's O-E-R, yeah. He discovered the connection. Now, what he had was a pretty simple little experiment. He had a compass, and he had a wire with current in it. And if you have a compass, you know, there's this needle there on the compass. I've got one, and I think the north end is red, like that, on my my compass. And what Ørsted did was he had a wire with current on it, and this current, here's this wire, and the wire had some current in it. Here comes the current in this wire. And he noticed that the needle deflected. It did this. And then when he disconnected took the current out, he had a primitive battery. They had batteries back in those days. When he disconnected the battery and there was no current, then the needle returned to pointing north, like that. This is the first time anybody had ever made a connection between the two different things, the electricity and magnetism, but they're very much related to one another. And we're going to discover the relationships between electricity and magnetism. So let's start with that. Are there any questions so far? Let's see who we got on board here. We have Zach, Phoebe, Daniel, Christy, and Nicholas. A good crowd. Had a good class there. Okay. Well, let me erase all this because we're going to talk about some of these relationships with magnetism, particularly magnetic force. Now, electric force, let's go back and talk about electric force for just a minute. Electric force is pretty simple. It's just F equals Q times E. If you know the electric field, and we've studied electric fields, haven't we? We've got equations for electric fields around wires, plates, discs, solenoids. We've done all sorts of stuff with electric fields. And you know what an electric field is. It's force per unit charge. Now that force is an electric force. It's an electric force. And you can get, this is the definition of electric field. You all know that. And you can get from here to here quite easily. Just a little algebra step there. And electric force is pretty simple. Electric force is just F equals QE. Now, gravitational force is pretty simple. Let me talk about that for just a second. Gravitational force. Is that how you spell gravitational? Yeah, I think so. It's pretty simple. It's just, and you know what it is. It's F equals mg, where g is gravity. It's simple too. You have to know what the mass is to know what the gravitational force is. And you have to know what gravity is. Now here in Tulsa, we use this value of 9.81 for gravity. That's pretty darn close. So those are pretty simple, but see, magnetic force, it's a little more complicated. It goes like this. You'll find this on page 501. Page 501. Gravitational force. No. Magnetic force. See, this is magnetic force. You can put a little M there if you want. Now, you all know what F is. That's force. That's magnetic force. You know what Q is? That's charge. We've been using Q for charges. Now, V is velocity. To have a magnetic force, you got to have velocity. You have to have a charge that's moving. Remember in Orsted's discovery, he had a wire with current in it? Well, if you have a wire with current in it, you have charges that are moving. Now this B here is called a magnetic field. This has got an electric field, gravitational field. I'll tell you what the gravitational field is. It's your gravitational force, put a little g there if you like, divided by your mass. That's your gravitational force, or field. And you know what that's equal to? It's equal to gravity. But this B here is your magnetic field. E is electric field. B is magnetic field. And this equation really defines the unit for magnetic field. They decided to give it the name Tesla. See, magnetic field is measured in Teslas. Or you could just go T. There you go. The T there stands for Tesla. Now let's look at our units here. Let's look at our units. You know what force is in. It's in newtons. You know what charge is. That's in coulombs. Velocity is meters per second. And they decided magnetic field is in Teslas. So what's a Tesla? Well, you can figure it out pretty easy. A Tesla is a Newton divided by a Coulomb per second times a meter. And you know what a Coulomb per second is? That's an ampere, isn't it? So you could write this as newtons per amp meters. I think you'll see it written like that a lot of times. A Tesla is a newton. This is in your book. You could read your book. It's on page 501. And a Tesla is a newton per amp meter. Now this equation right here, it doesn't have a name yet. Like Newton's law or Hooke's law, or the Biot-Savart law, or I can't think of any others, but it doesn't have its own fancy name yet. But I bet that they'll honor somebody, maybe one of you guys. When you become famous for inventing something in the realm of physics, maybe they'll call that equation, here, let me think of a good name here, just a minute. Maybe they'll call that equation the Saltmarsh equation. Wouldn't that be a nice name for it? Saltmarsh equation. There you go. Yeah. Who else we got with us here? Just a minute. Hey, how about it? The Wilson equation. That's got a nice ring to it. They just don't have a name for it yet. I predict they'll name it after some famous person eventually, but they're not there yet. Well, let me show you one little more tiny bit of theory, and then we'll work some problems, and then we'll do some more theory. Now, what this is the force on a moving charge. See that Q there? That's in coulombs. But you watch here. I'm going to do a little algebra trick now. I'm going to write it like this. Your magnetic force is equal to Q times, see, velocity is just L over T. It's a distance over time, isn't it? We make a vector out of your distance. And we need to talk about this. This is a vector cross product. But first, what I'm going to do is I'm going to scoot that time under the Q like this and go Q over T, L cross B. Now, does anybody know what Q over T is? Let me ask somebody. Let's see here. How about my friend Christy? Christy, unmute and say hi. Earth calling Christy. Come in, Christy.
Hello. Can you hear me?
Hello. Hey, Christy. Q over T. That is something that we know and love. What is it?
Charge over time?
Yeah.
I don't understand what you're asking.
Charge over time. That's equal to something that we know and love. What is it? You know this.
I might, but it's not coming to me right now.
What if I told you that charge over time is current?
Oh, that makes sense.
Yeah, it's current. It's the amount of coulombs per second. That's what an ampere is. So see, you could write this. Isn't it funny, Christy, how your mind goes blank when somebody asks you something?
Yeah, it's usually the way it works.
That's how it works. You could write this as IL cross B. Now, how do they write it? Let me look in the book here. Let me shop around to see if I can find this. I'm looking for it. I don't. Yeah, there it is. Yeah, there it is. I see it. It's on page 5. This equation that I'm going to write is on page 512. And it's not named after anybody either. Now, they use it with a little L for some reason. I like the big L, but we'll do it their way. And they've got the force the magnetic force is equal to the current, Q over T, times L cross B, or that's a cross product. And you'll see that on page 512. Maybe we could do a problem on that. Before we do, though, I need to review some basics about the cross product. Let me talk about the cross product for just a minute. Did any of you have a comment or question before we discuss cross products? Well, okay. The topic right now, so that we can understand these equations. Here they are. These equations give you magnetic force. This is the magnetic force of a moving charge. This is the magnetic force on a wire carrying current that is in a magnetic field. But we need to talk about cross products a minute. Cross
Can you hear me?
product.
I have a question.
Yeah, I'm listening.
Okay, I didn't know if you could hear me.
Yeah.
So you said there has to be moving charge, and I think I should remember this, but I don't remember how that applies to bar magnets. Bar magnets?
Yeah.
Like they
yeah,
have
yeah.
a magnetic
Yeah,
force.
now thanks for bringing that up. Now, is that my friend Phoebe? Is that who that is?
Yeah.
Okay, Phoebe. If you have a bar magnet like this, Phoebe's brought up an interesting thing, and you have another bar magnet like this, and if you have the two north poles like that, they will repel. And so you can get a magnetic force. These magnets are going to take off. That one's going to go that way. That one's going to go that way. And so you can have magnetic force without any moving currents at all, like Phoebe is trying to tell me. And you're absolutely right. You don't need a moving current, and you don't need current in a wire either to have a magnetic force. Now, if it's the other way, if this is a south pole and that's a north pole, well, then they will attract, and they'll go together. Kind of like the magnets on your refrigerator. I've got magnets on my refrigerator, and there's a magnetic force that attaches that magnet to the refrigerator. But what these equations are dealing with is moving charges or currents in a magnetic field. Now, there's magnetic fields here. In fact, it goes from north to south. Magnetic fields always go from north to south, and there they are. There's your magnetic fields. Phoebe, are you okay now?
Kind of. I just don't know. Is there a different equation that we use when we do those, or?
No, we don't need an equation because we're finding forces on moving charges right now. And
Okay.
there are no moving charges there.
Right. So if
Well,
there's no moving
actually,
charge, but there is a field.
Yeah, there's a magnetic field. Actually, I'm lying to you. There is moving charges because these magnets are made up of molecules that have electrons. And those electrons are spinning. They're moving. They're spinning around their atoms.
Right.
So there are moving charges. And in fact, that's the reason why there's the magnetic force is because those electrons are moving inside your molecules.
Okay. I mean,
But,
it makes more sense now when you put it that way.
yeah, thanks for bringing that up. But now let's go back to some basics about cross products. If you have two vectors here, the cross product is it's equal to the magnitude of A times the magnitude of B times the sine of the angle between them. I bet you've seen that before. See, it's different than the dot product. The dot product is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. Now, another difference is the cross product gives you a vector. You need some sort of little unit vector here. There's different ways to express a unit vector. This is sort of a generic unit vector. See, it could be I, J, or K, or it might be in a oddball direction in 3 dimensions. This one's called the vector product. It's the vector product. Whereas this one's called the scalar product. You don't get a unit vector to multiply by it because it's a scalar. It's not a vector. The scalar product gives you a scalar, but the vector product gives you a vector. Hey, that kind of makes sense. Now, if you're in 3 dimensions, you have to use a determinant. I bet you guys studied this in school. Back when you were younger. I won't say better looking because you've always been good looking. But in my case, younger, better looking. But see, you have to use a determinant where here are the components of your 2 vectors. And this thing here is called a determinant. And I bet you learned it in school. Now let me ask one of my excellent students here. Let me go to my friend Daniel. Daniel, unmute and say hello, please.
Hello.
Daniel, when you were in school many years ago, did they ever talk about determinants, Daniel?
Yep.
Was that a yep?
Yes.
Yeah, they did determinants, yeah. You betcha they did. Well, if you're in 3 dimensions, you have to use a determinant to get it. Unless it's so simple, like if it's in X, Y, or Z, you don't need a determinant. And they taught you how to do it. We'll do some examples here in a minute when we do our problems. Okay, well, we talked about the cross product. And we've talked about these 2 equations that don't have a name yet. And now we're going to work some problems. The first one I think I'll work is 1137. Help me find 1137. I'm looking for problem 1137. Okay, it says a DC power line for a light rail system carries 1,000 amps at an angle of 30 degrees to Earth's magnetic field. What's the force on a 100-meter section of the line? Well, guys, on this problem here, we're going to have to use this equation here. and they gave us the current. Right now we're doing problem 1137. In my book, it's on page 532. And they gave us the current. They said the current is 1,000 amps. Okay. 1,000 amps. Now what's the length? 100 meters. The length is 100 meters. What's the magnetic field? It's the Earth's magnetic field. 5 times 10 to the minus 5 Teslas. That's sort of an average value for the Earth's magnetic field. And they want to know what the force is. But they said that the current is 30 degrees to the Earth's magnetic field. So here I'll try to draw it for you. Let's say this is your current. There goes your current. It's 1,000 amperes. But see, the Earth's magnetic field is doing this. And it's at an angle of 30 degrees. And so when you use this equation, you go the magnitude, you go the current times the magnitude of your length times the magnitude of your magnetic field times the sine of the angle between them. The angle between the magnetic field and the length, here's a wire with a length L. It's 100 meters long. And you have to multiply by the sine of 30. Okay. They want to know what the force is. And I will be quiet for a minute. And I want you to find it. Find the magnetic force on that, well, it's actually kind of a railroad line, isn't it? Let me read this again. Yeah, we're talking about like a railroad. Okay, go for it. Put that in your calculators. And tell me what you get. Well, I got an answer. Let me ask somebody here. How about my friend Zach? Zach, unmute and say hello, please.
Yeah, I got 2.5.
That's what I got.
Newton,
Good
right?
going. Zach, 2.5. But what's the units?
Then we'll do Newtons.
It would be newtons. That is correct. It would be newtons. Now here's where we need to find out the direction. Now you could get the direction using that determinant business. You could. Let's see if I can do that. That's certainly the hard way to do it. The other way to do it is with your right-hand rule, which is explained in this chapter. But we'll do it several ways. One way is with the, see, that I is just a scalar, it's just a magnitude, it's 1,000 amps. And here's where we're going to have our determinant. Now we need to decide on our directions. This is going to be X. This is going to be Y. And Z is going to be coming out of the board at you. Okay. Well, it looks to me like the length, the 100 meters, is entirely in the I direction. It doesn't have any J or K direction. See this 100-meter length? It's along the x-axis, so it's got 100 meters. You put a little meter right there if you want to have room, maybe. But there is no J, there is no K. Now, when it comes to the magnetic field, though, the magnetic field, it's got a X component and a Y component. Now, the X component is 5 cosine of 30. It's, we don't have enough room here. It's 4.33 times 10 to the minus 5 Tesla. You know what? I could make those micro Teslas. If I made that smaller, I could make that bigger. Let me do that. It'll give me a little more room. 43.3 micro Teslas. Now, in the J direction, it's 5 times 10 to the minus 5. It's got a component of times sine of 30. So that would be 5. Well, it'd be 2.5 micro Teslas, and it doesn't have any K component. So you are looking at the determinant there. I think I'm making this too hard.
Yeah, I was about to ask you what was happening. I'm kind of getting lost.
Say that again, please.
I was about to ask you what was happening. I'm kind of getting lost. What was where are you getting these? What math are you?
Yeah,
doing?
I didn't explain it very good. Let me try again.
All right.
Let me try again. Let me draw this. This is my vector B here. Let me make it bigger even. And I'll try to explain this better. Now that B is equal to 5, well, it's equal to 50 microteslas. See, if you make that smaller, you got to make that bigger. And what I need here is the components. I need these components. This component here is going to be 43.3 microteslas, and this component is going to be 25, not 2.5, that's wrong, 25 microteslas. See, those are the components. Zach, do you know how to make components?
Yeah, I know what you're talking about.
Yeah, you go B cosine of theta, there's your theta. So you go B cosine of theta. That'll give you your X component. Your Y component will be B sine of theta. And if you'll do that, where theta is 30 degrees and B is, what is it, 50 microteslas, you'll get these values. Now I need to make this big enough to where you guys can see it. Let me spread this thing out where we can fit all this information in here. See, this is 25 microteslas. This is 0. This is 0, and that's 0. So there's your determinant. Now, I don't know if you remember how to do determinants, But they taught me in school many years ago that what you do is you take your I and you cross out your row and your column, and then you take the minor. 0 times 0 is 0, minus 0 times 25 is 0, so there is no I component. This is going to give you 0 I. And then to do the J component, you cross out your column and your row, and then you do your minor. You take 100 times 0 minus 0 times 43. Then you get 0. There is no J component of the magnetic force. But when you do the K, here's what you get. In the K, you cross out your row and your column, and you do the minor. You take 100 times 25, subtract 0 times 43, and what you'll get is 2,500 microteslas But now I'm forgetting something. I'm forgetting my current. See, all of this is just this part here that we worked on. You have to multiply the whole thing by 1,000 amps. And here's what you'll get. You'll get 0I, 1,000 amps times 0 is 0. You get 0J. But see, when you take 1,000, I can't do that in my head. What's 1,000 times 2,500 e to the minus 6? I'm getting 2.5. 2.5 K newtons. Well, that's what we got. We got the 2.5 K a long time ago. But see, this gives you the direction. It's 2.5 K in the Z direction. Here's X, here's Y. Z is coming out of the board. And so there's a force on this wire that will move the wire out of the board of 2.5 newtons. Now this is the hard way. You don't want to do it this way. You want to do it with what they call the right-hand rule. So let's do it with the right-hand rule. Now they explain the right-hand rule in this chapter. Let's see if I can find it here. I'm snooping around trying to find the right-hand rule. There it is. It's on page 502. There's more than one right-hand rule, guys, but there's one of them on page 502. Before we do this problem with the right-hand rule, are there any questions on it yet? Tell you what, let's see if we got it right. Let's see if that's right. Look up 1137 in the back with me. Help me find 1137. And they said the answer is 2.5 newtons. They don't even give you the direction, but we've got to know how to do the direction. We got the right answer. We got the right answer 2 different ways so far. And now we're going to do it with the right-hand rule. Unless there's a comment or question. All right, here goes. I just need the room. There's some room over here. Now, one way to do it is the way they do it. They take their right hand, you got to use your right hand, you can't use your left hand. And they take their fingers and they they move their fingers in the direction of this L. I'm gonna have to stand up to do this. This is, it's explained on page 5, what did I say, 502, yeah. There's a nice picture. There's a nice picture on page 502. These are the vectors. This I here, that's not a vector. That's just a number. That's the amount of amps that you got. But this L, they made a vector out of it. It's in the direction of your current. The current's going to the right. So I want you to put your fingers on your right hand, pointing to the right, because that's where the current's going. And then your magnetic field is a vector, and it's going up this way. So what you do is you take your fingers and you turn them to where they'll be going. Well, you take your whole hand really, and you move it to where they'll go where the magnetic field is. Your thumb will give you the cross product. In this case, the force. See, here's L, there's B, and there's my thumb going out of the board in the K direction. Now I could show you several other right-hand rules, but not yet. We'll just go with that right now. Any comments or questions on that one? Well, okay. Let's do a different one. And which one did we just do? Did we just do 1123? Is that what we just did? I got lost there, guys. No, we did 1137. Let me mark that one out. We did that one. Okay, let's do a different one. Yeah, now this one looks pretty good. This one is 1123. Let's see if we can do 1123. I'm going to just erase all this stuff here. Okay, now right now we're looking at 1123, and I've got to find it. Let me snoop around here and find it. Just a minute. There it is. An electron moving at so-and-so meters per second in a 1.25 Tesla magnetic field experiences a magnetic force of so-and-so. What angle? What angle is there? Now on this problem here, they're going to use this equation here. See, before on that problem we just did, we used this equation here. This is the equation you use when you have a current in a wire. This is the equation you use if you have a moving charge in a magnetic field. Okay, now let's see what they said here. I'm trying to do problem 1123. They said it's an electron. Well, we know what the charge is on an electron. It's 1.602 10 to the minus 19 cool. You need to write that down where you can get it in a hurry. Look, we know what that is. Do they tell you the velocity? Read it here. It says magnetic force. Yeah, they give you the velocity. Okay, well, let's write that down. They said the velocity is 4 times 10 to the third meters per second. If you're wondering what we're doing right now, we're just working some problems. This one is 1123. It's on page 530 in my textbook. And look at here, we've got the velocity. That's nice. Now what else? Let me keep reading. Oh, 1.25 Tesla magnetic field. Hey, they give you the magnetic field. This B here is a symbol for magnetic field, and it's 1.25 Teslas. Tesla is the unit for magnetic field. Okay, great. We know all that. So what? Oh, they even gave you the magnetic force. Look here, they give you the magnetic force. Look, they give you everything, don't they? Let's write that down. The magnetic force is 1.40 times 10 to the minus 16. It's not a very big force, guys, but I can't help it. Now they want the angle that the velocity of the electron makes with the magnetic field. They need the angle. Well, I bet we can get that. Here we go. Let's write all these numbers down. This one's 1.40 times 10 to the minus 16 newtons. This one is 1.602 10 to the minus 19 coulombs. This one is 4.00 times 10 to the third meters per second. And this one is 1.25 Tesla. But you know what we're missing? We're missing the sign of theta, aren't we? Because remember, when you have a cross product like of two vectors, that's equal to the magnitude of that one times the magnitude of that one times the angle between them. So you have to multiply by the sine of theta. Here's a nice equation, look. Here's a nice equation with only one unknown. I'm going to shut up for a minute. I want you to find the angle between the velocity and the magnetic field. Go for it. Well, I don't know if I did that right or not. I'm going to call on some of my students to see what they got. Let me call on one of my students. Let's see. Who? I don't want to pick on you if I pick on you too often. I think I've already picked on several of you. Phoebe.
I can offer. I don't know if I'm anywhere near correct, but I've got theta would be approximately 10.1 degrees.
That's what I got. Good going. If you plug all that stuff in, theta is, well, I got 10.0, maybe 7 or something like that.
Yeah, yeah.
Like,
I didn't know
like
how far
Phoebe
was
said,
around.
10.1 is fine. Good going, Phoebe. Proud of you. Well, what does that mean? That means that it's not a very big angle. That means if you had a magnetic field here, I'll draw you a magnetic field. There it is. That means that this electron is moving not at a very tiny angle. It's kind of going like that, where this angle here is only 10.1 degrees off of the magnetic field. Okay, well, let's see how we did. Go to the back, look up the answer for 1123, and let's see what happens. 1123. They said 10.1 degrees, but now they gave us two angles. They also said 169.9. Now, what that is if the electron was going like this, like that, see this angle here, that's 169.9. If you add these two up, you get 180, right? I think so, yeah.
Yes.
Does that make sense? So we don't know which way it's going because they didn't give us the details, but there's two answers. When I did this, 10.1 degrees, I got something, when I did all this stuff, I got sine of theta is equal to something like 0.175. And so when you take the arc sine, you get the 10.1. But if you take the sine of 169.9, you get the same number. Try it. Take the sine of 169.9 degrees and see what you get. Let's see. Sine, you have to take the sine. 169.9 degrees. The sine, yeah, you get the 0.175. See, you get the same thing. So the theta could be 10.1 or it could be 169.5. Did that make sense? I hope so. Okay, well, good. We did that. Let's do another one. Okay. Let's try this one. If you're happy, I'm going to erase this. Speak up because I'm going to erase it. All right. Now, the one I want to do now, let's do one more problem and then we'll have some more wonderful theory. Doesn't that sound good? This is problem 1165. Let me find it here. 1165. Okay, I found it. An electron moves with a velocity, blah, 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 enters a region where there's a uniform electric field and a uniform magnetic field. Magnetic field is given by blah, blah, blah. If the electron travels through the region without being deflected, what is the electric field? Now, here's what they're saying. You've got an electron. There he is. He's zooming along here. And he encounters an electric field and a magnetic field. Now the force, the electric force, is equal to E, well, it's equal to QE. We talked about that earlier. Electric force is equal to QE. Now, magnetic force is equal to QV cross B. See, these are really vectors. You can make vectors out of all of these. Now, what they're telling us is that the electric force and the magnetic force cancel each other out, and so the electron just keeps traveling straight on through. It's not veered off of its course at all. So what we're going to do is we're going to say the electric force on that electron is equal to the magnetic force on that electron. And they're equal and opposite. I guess you could put a minus and set it equal to 0, see? But I'm going to put an equal sign here in the middle. The magnitudes of those two are the same, but they're in opposite direction, if that makes sense. Well, you know what? We could lop off that Q. We don't even care about it. What we care about is what's left. Okay. Well, what do we know here? Let me read this again. We're doing 1165. I'm on page 534 right now. And it says here, the velocity is 4I plus 3J plus 2K. So they're going to give us the velocity. I'm going to circle it. There it is. We've got it. Oops, wait a minute. Times 10 to the 6th. And the units are meters per second. All of this is times 10 to the 6th. That's going pretty dang fast, you know it? The speed of light is 3 times 10 to the 8th. So we're somewhere in the neighborhood of 1/100th the speed of light, which is still pretty dang fast. Well, there's the velocity. It enters a region where there's a uniform electric field and a uniform magnetic field. The magnetic field is given by 1I minus 2J plus 4K. Times 10 to the minus 2 Teslas. Hey, look at here. They gave us the magnetic field. What are we supposed to find? Well, we're supposed to find the electric field. Well, we got a nice equation. Look, the electric field is equal to V cross B. All we got to do is that determinant. So let's write that determinant. Here goes. We're going to write that determinant. If you're rusty on determinants, you get out your old high school algebra book. And it'll tell you all about them. All right, here we go. We want V cross B. Well, you have to multiply by Q. No, you don't. No, you don't. No, an electric field is that you don't need the Q. We got rid of the Q's, remember? It's just V cross B. So here's our determinant. I'll try to make it nice and big. You got I, J, and K. And you got 4, 3, and 2. Now I know they're times 10 to the 6th. We can just multiply everything out here by 10 to the 6th and we'll be okay. And then they have 1, minus 2, and 4. 1, minus 2, and 4. And there's a 10 to the minus 2. We're going to have to multiply by 10 to the minus 2 when we get all done. And we'll be done. Yay, we can do that. Okay, now here's your chance to do a determinant for me. I kind of showed you how to do them, and you might have forgotten. Remember, what you do is you cross out the column and the row, and you do the minor. You go blah, blah times that minus blah, blah times that. I'm going to shut up, and then we're going to write the answer. Well, let's see if you can do it. Let's see if you can remember how to do determinants. If you can't, well, I'll do it. Maybe you'll remember. Okay, go for it. Find the electric field. Go. Well, I don't know if I gave you enough time, but we got a lot of stuff we want to learn tonight, so let's go ahead. Now, if you cross out the column and the row and go 3 times 4 is 12, minus 2 times minus 2, that's going to give you 16i. So far, so good. And when you do determinants, you go plus, minus, plus. If there's more, they alternate. So we're going to have to go minus j, but here, cross out the row, the column, cross out the column, cross out the row. And what you'll have is 4 times 4 minus 2 times 1. I think that's 14. But since they alternate the signs, it should be minus 14. Come on now. Minus 14j. Now let's do the k. Cross out the row, cross out the column, go 4 times minus 2 is minus 8. Minus 3 times 1, I think that's minus 11. Unless I've goofed it up. Now you still have a 10 times the minus, or 10 to the 4th, see? You're still going to have to multiply all of this stuff times 10 to the 4th. And the units for electric field are newtons per coulomb. We really should go through the units here in a minute, but I think we're done. I think that's the answer. Let's look and see how we did. This is problem 1165. Go to the back and help me find 1165. 1165.
That's what I got.
Okay, now what they have is different. They have 1.6 I minus 1.4 J minus 1.1 k times 10 to the fifth. You know what, though? It's the same. They made this bigger, and they had to make these smaller. It's the same thing. And instead of going newtons per coulomb, they used volts per meter. But we know electric field can be expressed in newtons per coulomb or volts per meter. We've studied that, and we're happy with that. Hey, we got the right answer. If you are rusty with that, and get out your old high school algebra book and study it. Now, I'll show you there is another way to do this. Let me see if I can show you the other way. But we got it. We got the right answer. We're happy. I just need a little room here. There's some room up here. Let me show you another way of doing this. You want to multiply these two things. Now, I know there's going to be a 10 to the fourth when you get all done. We can put that in front if you like. 10 to the fourth times whatever I'm going to do here. Now, what I'm going to do is I'm going to take that 4i and I'm going to multiply all of these. I'm going to have 4i times 1i. That'll give you 4i cross I. Well, I cross I is 0 because the sign of 0 is 0. So that gives you nothing. I don't know if that made sense. And 4 times minus 2 is minus 8. I cross j. Well, I cross j is equal to k. I'll show you why here in a minute. Then we're going to go 4 times 4, I cross k. Well, that's 16. I cross k. I think that's equal to a minus j. Here, let me write my little thing here so I'll know. The way it goes is like this. I cross j gives you k. J cross k gives you I. K cross I gives you J. Going clockwise is plus. Now, what I have here is I cross K. Well, see, when you go counterclockwise, you get a negative K. So what I'll have here is negative 16. No. I cross K is a negative 16 J. Yeah. What happened here? I got lost. Just a minute. This should be minus 8K. Yeah, here we go. And this is 16I cross K, but it turns out to be a minus 16J. Because when you go I cross K this way, you get a minus J. Okay, now we're going to do the 3 times this. 3 times 1 gives you 3, J cross I. Well, J cross I is going this way, and that gives you a minus K. All right. So you get minus 3K. Need a little room here. I'll just scoot on down. And then I'm going to go 3 times minus 2. That's minus 6J cross J, but that's 0. See, J cross J is 0. And then I got 3 times 4 is 12, J cross K. Well, J cross K is I, so you got plus 12I. This is the hard way to do it, but it's another way to do it. Now, we got one left. 2 times 1 is 2, K cross I. Well, K cross I is J, so you got plus 2J. And 2 times minus 2 is minus 4, K cross J. Well, K cross J is a minus I, but you got a minus. And so it's a plus 4 plus 4, k cross j is plus 4i. And finally, you have 2k cross 4k. That gives you 0, and so you're done. You can put a 0 there if it makes you happy. Okay, let's combine all this stuff. What do you got in the way of k's here? You got minus 11k. What about j's? It looks like minus 14 j's to me. And what about i's? Where are my i's? There's 12i and 4i. That makes 16i. Well, by Jove, look, 16i minus 14j minus 11k. It's the same doggone thing times 10 to the fourth. You get the same answer by doing this little thing we did here. Now, I've seen this done different ways. Some people prefer this. They go I, J, K, I, J. And the way it works is I cross J is K. J cross K is I. K cross I is J. Now, going back the other way, J cross I is minus K. I cross K is minus J. K cross J is minus I. I could write that out for you if you didn't follow it. Just speak up. Do you have any questions on problem 1165? Well, let's look at the let's look at those units, and then I think we need to take a little tiny 10-minute break is what I think. Now the units. I erased it there, but I think what we had before I erased everything was E was equal to V cross B. If that's not right, speak up, somebody. And see, the V is in meters per second. Here, let me write that down. Well, there it is right there. Look, there's your meters per second. And the B is in Teslas. So here, let's look at the units and make sure these units are okay. Meters per second times Teslas. Now what we hope is that we'll get newtons per coulomb, or the way they did it, they got volts per meter, but it's the same thing. But let's make sure that's right. Now a Tesla, earlier tonight, we found out that a Tesla is a Newton per amp meter. Watch the video, the YouTube video over again. We talked about that. Hey, look, the meters cancel. And look, you have an amp times a second. You know what that is? That's a coulomb. See, an amp times a second is equal to a coulomb. So you know what you got here? You got a Newton per coulomb. Yay! So the units worked. And we got the right answer. How about that? And I showed you about I, J, and K. Did you have any questions on that?
No.
Okay, well, let's do something else then. I tell you what, let's do. Let's take a 10-minute break, and we'll come back and we'll have more fun. I'm gonna go see what's in the refrigerator. We'll be back in 10 minutes for more fun. Go get up and stretch for a minute. It'll be good for you. We'll be back. Well, now I gave everybody, I guess we're back. Let's see if we're back. Well, it looks like there's 5 of us anyway that are back. was I going to say? I gave everybody the laboratory description for Thursday. It's called, oh gee, the name of it is Current Balance. We are going to do, go ahead.
I forgot to grab mine before I left.
Dang. Well, I tell you what, if I can think about it, I'll put one on the blackboard. But it's
That would
not the
be
end.
awesome.
It's not the end of the world. If I forget, I'll be glad to give you an extra copy. But yeah, I'll try to remember.
Thank you.
Oh, anytime.
Either way.
It'll be fine. Just get some good lab partners to help you. I know you have them. Okay, now let's see what we're going to do now. It's a slightly different topic. We're going to talk about, well, first of all, let's talk about the Earth's magnetic field. Inside the Earth, you probably know there's a molten magma. Is that what they call it? I'm not a geologist, but it moves, it swirls around. It has charges. It has electric charges, and they're moving. They create a magnetic field, and there's a picture of it on page 499. They have a picture of the Earth. And you know, there's an equator that goes here. And there's a North Pole up here. And the South Pole down there. But the Earth also has a North Magnetic Pole. It's not at the the geographic North Pole. It's kind of up here in the magnetic pole. It's up there near Hudson's Bay, way up north in Canada, actually. And what's weird about it is it's a south magnetic pole. You know how you have south poles and north pole magnets? Well, the magnetic pole of the Earth right now is a south magnetic pole. And so if you have a compass that has a north and a south pole, the North Pole is attracted to the south magnetic pole of the Earth. That's how come it points north. Interesting. Well, we could talk more about that, but some interesting things happen because of the Earth's magnetic pole. There's charges from outer space that are entering the Earth's atmosphere all the time. Some of them come from the sun, and some of them come from outside our solar system. Those are called cosmic rays. But when they enter, for instance, it's kind of hard to show you this, but there's a magnetic field lines doing this. It's really three-dimensional. And if you have a cosmic ray coming in, here I'll draw this for you. If you have magnetic field lines doing that. And here comes let's say it's a positive, like a helium nucleus. It's positive. Here it comes. How does that work? The force on it is equal to QV cross B. And if it's got a velocity, here it comes. Here comes your little helium nucleus. It's coming this way. B's that way. And if you take the cross product, put your right hand rule, put your fingers in the direction of the velocity, and turn your fingers turn your fingers in the direction of the magnetic field. See your thumb? That positive helium nucleus will curve. In fact, it will go in a curve like that. And they describe this on page 506. Well, let's go to 506 and I'll show you what happens. Your particles can get trapped. Now they have their magnetic field going into the board. The X's represent the tail feathers of an arrow. See, if it was coming out of the board, you'd have your pointed arrow tips coming out at you. But with the X's, those are like arrows going into the board. And they have they've got a negative charge like an electron, but we'll just have our positive charge. Let's say we have a positive charge and it has a velocity like that. Okay, take your fingers, have the fingers in the direction of your velocity. Here, let's write this. Your magnetic force is equal to Q V cross B. And we want our fingers in the direction of the velocity, and then turn them in the direction of your magnetic field. It's going into the board. We see where your thumb is? Now, let me put that force. That force is going to go this way. See, the velocity is doing this. It's going in that direction. The magnetic field is doing this into the board. And the force is going this way. So what happens is this thing curves and it's going like that now. Now let's see what happens here. Now the velocity is going this way. And see, the velocity is going this way. Get your fingers in the direction of the velocity. Turn them into the direction of the magnetic field, which is into the board. Ooh, the force on that particle is going down. So it curves. It winds up, it's going to go in a circle. See, when it's going this way, when the velocity is this way, it's going down. Here it was going, this was going down. Now get your right hand and it's hard for me to do. I'm no good at 3 dimensions. We've got to turn, somehow we got to turn that. How do I do that? Just a minute now, let me think. The velocity is going down. I have to stand up to do it. I can't do it sitting down. I don't know if you can see this. There's all my papers. But see, the velocity is going down. Magnetic field's going in, so you turn your fingers and see where my thumb is? That means the force is going that way. But this thing's going to go around in a circle. It gets trapped. When these ions enter our atmosphere, they get trapped and they go around in a circle. And so it curves, and now it's going this way. So now it has a velocity this way. Get your fingers going. Again, I don't know if I can do this. I have to stand up. You get your fingers going this way, turn them that way where the magnetic field is. See where your thumb is? It's going up. So this one has a force going up, and it goes around and around in a circle. Now you've studied that, and you know when something goes around in a circle, it's equal to mv squared over r, where this is called the centripetal acceleration, and this is called the centripetal force. You go around in a circle. And so what you can do is you can set this centripetal force equal to your QVB. Now there's a sign of 90 because everywhere the velocity and the magnetic field are 90 degrees apart. The sign of 90 is just 1, so it just sort of disappears. You don't care about it. And you've got yourself a nice little equation now. We can get rid of one of these V's, and now we have this equation here, mv over r. See, r is the radius of this circle, equals QB. Let me box that up for you. Nice little equation. They explain it in your book on page 506. You could read about it. Let's do a problem involving that, shall we? Now, the name of this topic is the motion of a charged particle in a magnetic field. That's the name of it. See, we have a charged particle. In this case here, it was a positive charged particle. And it gets trapped and it goes around in a circle. Okay, well, let's find a problem dealing with that. This will work. This is problem 1153. Let me make a note of that. We're going to do a problem 1153. Let me erase all this except that equation. We might need that in here in a minute. Now this problem 1153. Let me find it now. I got lost. Aha. Well, this one is a cyclotron, so I need to explain cyclotrons briefly to you. We got time, we got an hour. I think there's a picture of a cyclotron in this chapter. Let me snoop around and see if there is. Yeah, they talk about it on page 523. what they've got, we'll talk about cyclotrons a minute, and then we'll work our problem. These are fairly recent things in history. I think the first one was in the 30s, 1930 something. Be interesting to read about it. But they have what they call 2Ds. There's one going kind of like that. These are, it kind of looks like a big D, doesn't it? And these things are hollow. That's supposed to be dashed. These things are hollow. And what they insert in here is a red hot wire. Red hot. They're connected to some voltage there. And the wire becomes red hot, and electrons are boiled off of the wire, just like you'd boil water. And if you make this D positive and this negative, the electrons will head that way. You can see that. But there's electrons going in all directions. So you got an electron, it's spearing off of here, and it starts heading this way towards the positive. But it will curve because you have a big magnetic field operating. I think the magnetic field is coming out of the board. You know, they can make electromagnets, huge electromagnets. And you know how the equation works. It's this equation here. Let's go back to this one briefly. If the velocity is going this way and the magnetic field is coming out of the board, then you would have, if it was a positive charge, you would have it forced to the right. But if it's a negative charge, if it's an electron, the force will be opposite. It'll be to the left. And so it'll start heading off. This force will make it curve to the left. These Ds are hollow. They're metal. They're hollow. And the whole thing is in the evacuated chamber with no air. They've pumped all the air out. And so these electrons are free to move without running into air molecules. And so it starts to go in a circle like we've been discussing, according to this equation. And when it gets to about here, they change the polarity. They make this one minus and this one plus. Actually, they have those Ds connected to a, it's a radio station they have that's, what's the name? It's a short wave. They have a short wave radio station, and the frequency is very, very fast. But see, they'll make this side positive. Well, that makes the electron want to go this way now, because that's plus and that's minus, so it's repelled. And it'll speed up. And because it speeds up, it'll go in a wider circle. And just the time it gets to right here, they time this and they make this one plus, this one minus, and it gives the electron a boost. It's kind of like when you push a kid on a swing. When he comes back, if you give him a push just at the right time, the kid will go a little faster, a little higher, and they'll come back. And if you push him just at the right time, you can get him kind of in a rhythm and swinging pretty high. This is connected to a shortwave radio station that's changing it from plus to minus, minus to plus at a very high frequency. we could discuss that, but the idea is it speeds up and it kind of goes in a spiral like that until it finally comes out here, and they have a window here that doesn't let air through, but it'll let electrons through. It's like a very thin piece of quartz, and you get this beam of electrons shooting out of this thing, and then they do experiments with it. So we've explained the cyclotron to you, and we're going to do problem 1153 now. Now let me find it. We're accelerating, we're not doing electrons though, we're doing protons to 1/10 the speed of light. Well, we're going to need the mass of a proton, so I'm going to look that up. The mass of a proton is 1.67 times 10 to the minus 27 kilograms. Aha, we just got the mass of the proton. Read on. If you just tuned in, we're doing problem 1153. The speed is 1/10 the speed of light. Well, the speed of light is 3 times 10 to the 8th meters per second. So 1/10 would be 3 times 10 to the 7th meters per second. So look at here, we got the velocity. Now let's keep reading. What else does it say? The magnetic field is 1.5 teslas. Okay. Magnetic field is 1.5 teslas. Yay, we got that. Hey, we know what the charge is too, because the charge of a proton is 1.602 times 10 to the minus 19 coulombs. Same charge as an electron. Look, we have everything except the radius. Maybe that's what they want. Let's read this. Determine the rotational period, the maximum. Well, part B is the radius. We'll get the period in a minute, but let's get the radius first. Okay, let's put in all our numbers. Here we go. And I want you to calculate the radius. And now here's our numbers. We have 1.6726 10 to the minus 27 kilograms times 3 times 10 to the 7th meters per second divided by R equals 1.602 times 10 to the minus 19 10 to the minus 19 coulombs times 1.5 teslas. Now here's our equation. There's only one unknown. See it? We know everything in this equation except R. So go ahead. I'll shut up for a minute. I'll give you a minute. Find the radius. Now what you're going to find is the maximum radius, because this is the maximum velocity. They're accelerating that thing to 1/10 the speed of light. So we're going to get the maximum radius. We're going to get this radius of our cyclotron. Go for it. Well, I don't know if that was enough time for you, but I got an answer. Let me go to one of my excellent students here. Daniel, unmute Daniel and say hello, please.
Hello.
Daniel, did you figure out what this R is in this equation?
I got 4.79 times 10 to the negative 35th.
Something bad happened.
Was that even remotely close?
No, it's way off.
Okay, hold on.
I don't know what you did, but it's way off.
Wait, is that negative 27 on the 1.672?
Yeah, it's a negative 27.
Never mind. I had.
You probably can't read my writing. That's probably what it is. That's okay. Let's try somebody else here. Let's see, that was Daniel. Well, we're going to try my friend. Gee, some of us have peeled off. There's only 5 of us left. I'm proud of you for sticking it out, though. Nicholas, unmute and say hello, please.
Hello.
Nicholas, have you figured out this radius?
I think it's 0.21 meters.
Yeah, I'm getting 0.2088 meters. Daniel, are you getting that yet?
Not even remotely close. I'm solving for R, right?
Yes.
What did you get, Nick?
0.208 meters.
Oh, yeah, okay. Because I changed it to centimeters, so I was confused for a second. Okay.
Well, you could call it 20.88 centimeters if you wanted to. Okay, I wonder how we did. Let's look at the answer book. This was 1153. Let's see what they said. They said 0.21 meters. The answer book says 0.21 meters, so I'm pretty happy with that. But now they wanted something else. Let me read the problem again. I got lost. We're doing 1153, and they wanted something else. They wanted the rotational period. Now, what they're talking about is how long it takes for these protons to make one circuit, to go all the way around the circle. Now they go really fast. I mean, they're going, what is it, 1/10 of the speed of light? Holy cow. But I bet we can get that. Period. They use this symbol here for period. It's kind of a capital Greek letter tau. That shows up good. Let me find another spot to do it in. How about over here? Here's a spot right here. The symbol they use for period is the Greek letter tau. Now what that period is, it's the distance all the way around, which is 2 pi r, 0.2088 meters, divided by the velocity. The velocity is 3 times 10 to the 7th meters a second. Does it make sense that if you take the distance and you divide it by the velocity, you get the time? So you're probably more used to this. You take the velocity times the time gives you the distance. Distance is equal to velocity times the time. I bet you've heard that before. Well, the time should be equal to the distance, which is the circumference, 2 pi r, divided by the velocity. All right, do that. Put that in your calculators and tell me the time. On your mark, get set, go. Well, I got a time. I wonder if you got what I got. I got 4.373 times 10 to the -8 seconds. I don't know if that's right or not. Did anybody get that?
Uh-huh.
I heard an uh-huh. Let me see what the book says. The book says 4.4 times 10 to the -8 seconds. The book says 4.4 times 10 to the -8 seconds. Holy cow. That thing goes around there pretty quick, doesn't it? All right. Well, we got the answers they wanted, and we talked about cyclotrons. Let's do another problem. Was there any question on 1153? Because if you're happy, I'm going to erase all this. All right. I told you they connected this cyclotron up to a shortwave radio station. Let me show you that real quick, and then we'll do another fun problem. I have a shortwave radio, and a typical wavelength is 40 meters. There's several bands. There's an 80 meter, 40 meter, 20 meter band on my shortwave radio. But see, that's the wavelength. And there's an equation that goes like this. The speed of light is equal to, boy, am I rusty. It's equal to the wavelength times the frequency. Now the speed of light is 3 times 10 to the 8th meters a second. And if the wavelength is 40 meters, you can solve for the frequency. Go ahead, I'll shut up. This would be a frequency that they could connect to that cyclotron. Go ahead and tell me what you get.
Remind me the units of frequency again. I feel dumb.
No, thanks for asking. It's megacycles on your FM radio. Like 88.6 megacycles per second.
Okay.
You got radio on your AM dial. what is it, about 550? But see, that's kilocycles. That's kilocycles. So what that is 550 times 10 to the 3 per second. That's supposed to be an S, if you can read my writing. But see what we got here, I did this and I got 7.5 times 10 to the 6. Some people call it CPS, cycles per second.
Okay, I just didn't know what units. I had an answer, but I didn't know what units to use.
It's kind of a weird unit. It's a second to the -1 because cycle is not it doesn't have units. It's just
Right.
one trip around. But man, if you think about it, that's moving on 7.5 million times a second that proton spins around there. That's kind of hard for us to understand. Okay, well, we're going to work another problem now, but thank you for asking. And this one's 1126. I'm going to erase all this so we can have some room here. Now let me find it. 1126. Found it. Viewers of Star Trek have heard of an antimatter drive on the Starship Enterprise. Do we have any Trekkies out there? We've got Zach, Phoebe, Daniel, and Nicholas that are sticking with us. Some of us have dropped out tonight. Are any of you guys Trekkies?
No, I never cared for the show.
I like it. I don't know if I could be considered a Trekkie.
Star Trek. Well, I think I've watched it. I think there's different version of it. There's one with Jane, Captain Jane something, and then there's one with Jean-Luc Picard, but I'm not an expert. Anyway, back to the problem. We're going to do problem 1126. And this Enterprise ship, Starship Enterprise, has a antimatter drive. They store this antimatter in a vacuum chamber circulating in a magnetic field. You know what happens if antimatter and matter get together? It's poof, and they're gone. A tremendous amount of energy is given off. There are those that think that half of the matter in the universe is antimatter. Like, for instance, suppose you get in a rocket ship and you go to a antimatter, kind of a twin of the Earth with beautiful oceans and everything, and you got all these lovely looking people. You might even get interested in somebody there and fall in love. But here's the problem. If one of you is matter and the other one's antimatter, be very careful, because if you get together, it's poof, tremendous amount of energy given off, and it's over. The romance doesn't last long. But it's a fascinating concept. And I'm reading this now. This is in your book. It's on page 530. You've probably heard of antimatter. Antimatter annihilates normal matter, producing pure energy. And they want to know what strength magnetic field is needed to hold antiprotons moving at 5 times 10 to the 7th. They're going to give us the velocity. Now, these are antiprotons. Now, what that means is they have the mass of a proton, which I erased. I had it up there. It's 1.6726 10 to the minus 27 kilograms. But they have the charge of an electron that's negative. See, it's weird. They're an antiproton. They're negative like electrons, but they have the same mass as a regular proton. Now, let me keep reading. They're moving in a circular path of 2 meters in radius. So here, let me draw that. These antiprotons are moving in a 2-meter radius circle. So, here's your velocity. You're going around and around in a circle. There you go, and you have a magnetic field going into the board. Is this, what do they want to know? Let me read this. They want to know what the magnetic field is and for them to go around in this circle. Well, we have the equation. It goes like this. There's our equation. Now, we know the charge. It's given here. Wait a minute, though. I've got these magnetic field going the wrong way. They're going to have to come out of the board. We know the velocity. It's right there. Do we know the magnetic field? Just a minute, I got lost. That's what we're supposed to find. We're going to try to find it. Now we know the mass. There's the mass of your proton. We know the velocity. There's the velocity. And we know look, we know everything, guys. Everything except the magnetic field. Okay. Solve it. I'll shut up for a minute. Put that stuff in your calculator and find the magnetic field necessary to trap these protons. See, we're going to have them in this vacuum where they can't touch the matter of our spaceship. Because if they do, it explodes. We don't want that to happen. So go ahead, I'll be quiet. I can write it out if you need me to. Well, I found what I think is the magnetic field that they need on that Starship Enterprise. Let me go to my friend. Well, gee, there's only 4 of you left, and I just keep picking on the same wonderful students. Phoebe, unmute and say hello, please.
Hello.
Hello. Phoebe, did you figure out that magnetic field yet?
I did, but I am trying to figure out what the units are.
What'd you get?
Tesla,
What'd you get for the number?
negative 3.83116.
That's not what I got.
Okay, I must have set it up wrong. I don't
I got
normally put it
negative.
all in at the same time.
Here, let me write it out.
I got negative 0.261.
Now the answer is 0.261. Do not get hung up about the negative sign.
Okay.
You have to figure that out with the right-hand rule.
All right.
If this is a negative charge moving this way, and the magnetic field is coming out of the board, it'll go counterclockwise. Just don't get hung up. But Phoebe, the unit for magnetic field
It's
is,
Tesla.
yes,
Tesla.
yay. And that is the correct answer. And if we look in the back of the book for the answer, let me see what the book says. The book says, well, they don't say. They don't do even numbers, do they? Oh, well. At
So,
some point- Go
when you
ahead.
set it up,
Yeah. You want me to write it out?
well, I mean, I guess
Yeah, let me write it out.
I figure out how to do this.
Yeah, here, I'm going to write it out. Here we go. There's plenty of room here. Now we're going to get rid of one of these V's. See that V squared? Forget it. See that V?
Oh, that would have been smart.
Yeah, it makes life a lot easier. Do you need me to keep going?
No, I think if I would have just put it in parts in my calculator, it would have been fine
You would have
and
been
do
fine.
that.
You would have been
Yeah.
fine. Okay, well, that was fun. Let's move on. We do have a tiny bit of theory left. It's getting hot in my room here. I'm going to have to open the door. And then we're going to hit our last little bit of theory, which is about torque on a current loop. Let me open this door here. That'll help me. Either that or turn on the air conditioning. It's a fairly nice day today. Okay, now this is a topic here. This topic is called torque on a current loop. It really is the principle behind an electric motor. Now let me find where it tells about it in the chapter. It's on page 515. It's on page 515. Okay. Now let's suppose you have a magnetic field. You know, it could be 3 Teslas or whatever. It doesn't matter. You could just make up something there. You got this magnetic field. and suppose you had a current loop. Here, I'll draw it for you. Current loop. And we need current in this current loop. So if you connected this up to a battery, you could have current going this way and around the loop like that, and around the loop like that. You could have some current, and then the little positive charges will go into the negative of the battery. That's where all little positive charges want to go. But see, we're going to have some force on these wires here. It's given by this equation that we have learned tonight. Now, if the L, and see, in this case, your L is the length of this wire. And it would be going this way. There's your L on this wire. We'll talk about this wire. And see, the B is going this way. Magnetic field is going to the right. Now, you could either use I, J, and K, which would be all right. See, if your traditional I is going this way and J is going this way, then this is J and this is I. Well, what's J cross I? Well, I don't know. I was showing you that earlier. One way is this little business here. You got I, J, K. You got I, J, K. And if you go J cross I, you get a negative K. You see it? Going counterclockwise, J cross I gives you a negative. That's equal to a negative K. This here should be a negative K. What does that mean? That means it's into the board. The force, now let me do it in red. The force on this wire right here is into the board. We'll look at the tail feathers of an arrow going into a board, into the board. Now let's look at this wire here. Now this wire is going down, and so our L vector would be going down in the direction of your current. So instead of going up, it's going down. Now B is still going to the right, but now you've got a minus J cross I. Well, minus J cross I will give you a positive K. It'll give you a minus K, positive K. So what that'll do is give you a force on this wire coming out of the board. This thing will spin. Can you see it? There's torque acting on that current loop. Now, if you didn't like the IJK business, you can use the right-hand rule. I got my right hand here. I'm going to put my fingers, down. Oh, gee. I got to stand up to do this. I've got my fingers going down in the direction of my L, or my current, and I'm going to turn my fingers in the direction of the magnetic field. See, it's L cross B. There's your fingers in the L direction. Turn. Look at my thumb. It's coming out of the board. See, the force is out of the board. Now, on this one here, the L vector is going up, so my fingers are going up. Oh, gee, I still have to stand up to do that, don't I? This is very awkward. But my fingers are going up in the direction of L. This time I'm going up. And then I'm going to turn that into, yeah, here we go. I could have sat down and done that. Never mind. I think I can do that sitting down. See, what I'm doing again now here is the L going up. Put your fingers going up in the direction of your L vector. Turn your fingers into the board in the direction of your magnetic field. No. It's
Professor Griffin,
late at night. I'm getting mixed up.
you
Magnetic
hear me?
field's going this way. I still have to stand up. I'll get it right. Just a minute. Okay, there's my L. I'm going to turn my fingers in the direction of the magnetic field. See where my thumb is? It's in the minus K. See that minus K? It's minus K. This thing will spin. It will spin like that. Now you might ask, well, what about this wire here? Well, the L vector on it is going to the left, and the magnetic field is going to the right. So what you have is an L cross B, which gives you a LB sine of 180. Well, see, the sine of 180 is, well, don't forget the I. The sine of 180 is 0. So these wires here don't give you any spin, but these wires do.
Can anybody hear me?
Say that again, please.
Can you hear me?
Yeah.
I can hear you.
Okay. I just was gonna talk to you about the right hand rule thing. Like,
Yeah.
I was taught one where, okay, so you take your index finger and your middle finger and your thumb.
I like that one. I like that one too. Is
Yeah.
that Zach I'm talking to?
Nick.
Nick. Nick, I really like that one. What you do is, I like that better than the way the book explains it. Here, let's do this one. See this L here? That L is going up. That's your first vector. This is not a vector. These are vectors, but this doesn't have a vector notation. It's a vector. That's your first vector. And you use your first finger. This is my first finger. And then B is your second vector. And this middle one here, be careful about doing this, practicing this on the freeway. You could cause road rage. But what you do is you hold your fingers like this. You put your first finger going up. You put your second finger, the second vector, going in, and you see where my thumb is? First finger going up. Now this is
Your index finger should be in the direction of current flow, and
Now
then
the
your middle
current's
finger
going
should,
it's going that way.
and then your middle finger should be in the
Yeah,
direction. of the finger.
yeah. I did it wrong.
And then your thumb is the force.
Yeah. Yeah. Okay. This one's going up. This one's going over. This is your first finger, and this is your second finger. First finger going up, that's the L. Second finger going to the right, that's B. Thumb, that thumb going into the board. See, it's going into the board. You might like that better. Now, who was I just talking to? Was that Zach?
Nick.
That was Nick. Nick,
Yeah.
is that how you learned it?
Yeah, that's how I learned it the first time.
Do it that way.
Yeah.
That way is a good one too. There's about 5 different. Actually, the one I like best is the right hand screw rule. Be careful about saying that. It sounds like you're saying screw you, but I'm not. I'm saying the right hand screw rule. And what that is you know how a right hand screw works. You put your screwdriver there. and you turn it. Now, if you turn it clockwise, it goes into like a wood board or something, whatever you're turning. If you turn it counterclockwise, it comes out. So you take this L and you turn it into B. So that's clockwise. See it?
Yep.
To take this L and to turn it into B, that's clockwise. So you're going into the board. You see it's into the board? They call that the right-hand screw rule. That's my favorite. But Nick, if you like this one here, that's a good one too. Anyway, there you have it. Now we're going to get the torque. We're going to measure the torque, and then we'll work a problem. I just need the room here to figure the torque. Now, you know torque is force times distance. And the force is the ILB. ILB. And the distance is the distance between these. Now, what they chose for their symbols for the distance was, see if I can find this here. I think they call this distance here A, and this distance here, they called it a B. So that's an I. That L there is really an A, you know it? And to get the torque, what you need is force times distance. No, wait a minute. No. The L is the B. There you go. See, this was the L. I'm getting mixed up. That's the L, it's B. And this is your force. And here's your distance between them. You got this force here, this force here. The distance between them is A. And so what it amounts to is AB. It's IAB times B. And you know what this is? That's the area of your loop. If it's A by B, well, it's just a rectangle. And so you get IAB. And here's your torque equation. It should equal IAB. Now see if they have that in your book. IAB. Yeah, they kind of disguise it. It's there, but it's a little bit in disguise. Look on the top of 517. And what they said there, let me make some room here. What they said there on page 517 is the torque on a current loop is equal to, I don't know why they get this minus sign. That's got me confused. I don't know what on earth they're talking about with a minus sign. Actually, I like this one here. The torque is equal to N if you have more than one loop. Does it make sense that if you've got a whole bunch of loops and they go around and around and around, maybe 50 of them, you're going to have to multiply by 50 because you're going to get 50 times the amount of torque than you would with just one loop. And then there's your current. There's your current. And see, this A stands for your area of your loop. That's your A, B. There's your B. And there's your equation. And I like it. There it is. Now this thing right here, they've decided to give it another name. They're going to call it mu. We've used, I think maybe we've used mu for other things in this class. I'm trying to remember. But this is actually a vector. And what they do is they take mu cross b, and that gives you the vector torque. They give a name to this. It's called the dipole moment, or the magnetic dipole. And what they do is they take your area. See, this thing has an area. That's what A is. And they make a vector out of it. If you have a loop like that with a current going around and around in it, it's got an area, and they make a vector. Whoops, I'm going the wrong way. They make a vector out of it perpendicular to your area, and they call that mu. It's a Greek letter mu. It's called the dipole moment. See, even atoms have dipole moments because they have current loops, which has an area and a current going around, like if you have an electron, for instance. And they come up with this equation for the torque of a current loop, where this thing has got a fancy name. It's called a dipole moment. You might want to read this in your text. We got time to work a problem, but it's on page 517.
I just wanted to say that looks a lot like an electric field, but it's not. It just looks kind of like a similar concept. Is it anything analogous?
We've had something very similar to that, Phoebe, but I'm forgetting now what it was. Do you remember?
Well, I thought I almost did. I thought it was something like, oh, what is that? Yeah, the eye thing.
Yeah. My mind is mush right now. It'll occur to me later. But yeah,
Okay,
it does ring a bell. Here, let's work one problem, and then the fun will have to come to an end. This one's an easy one. I think we can handle this. This is 1143. We might have to start off next week with explaining this better. But this is 1143, and it says here, the torque on a current carrying loop is tau equals NIAB. Well, that's what I was saying, yeah. Sine theta. Now, I didn't mention that because this is what you'd have if your area vector is perpendicular to B, because the sine of 90 is 1. But see, it might not be perpendicular. Here, let me show you an example. You might have a magnetic field going like this, and instead of having your loop perpendicular to it, see, that would be perpendicular. There's your loop, current going around it. It might be at an angle, you know, like maybe 45 degrees, for instance. If it's at 45 degrees, you got to put sine of 45 degrees in here. But never mind, let's get back to our problem. This is 1143, and it says the units of Newton meters must equal the units of amp meters squared Teslas. Verify this. Okay, let's do that. Torque, we know, is in units of Newton meters. The number of loops, that is dimensionless. That just is, if you have 20 loops going around, it's 20, but it doesn't have any units. Current is in amps. Area is in square meters. You see how wonderful these brackets are? That A there and that A there are different. That A stands for area. It's in square meters. And that A there stands for amperes. That's the unit for current. And then B is Teslas. This is dimensionless. The sine of an angle in radians is got no units. Now our job is to show that all of this stuff is Newton meters. Okay, I'll shut up for 1 minute and you do it. Just show me that comes out to be Newton meters when you get through. Well, okay, here we go. That's nothings. That's amperes. That's square meters. And a Tesla is a Newton per amp meter. We learned that earlier in the evening. Look here, one of those amps goes bye-bye. And get rid of that 2 there and that meter there, and look what you got left. You got Newton meters on the left and Newton meters on the right. So it works. It works. And you understand what each term is. This is called torque. Number of loops, current, area, magnetic field, angle between your loop and your magnetic field. Well, I wish we had enough time to work some more of those, but we don't. It's been fun though. Here's your chance, your last chance to ask me anything. Did you have a comment or question?
Have a good night.
Oh, you too. You guys be careful. And I will see you Thursday night for that lab on current balance. And I'll try to remember to put that on the, my mind is just mush tonight. Good night,
It's
students.
okay.
I'll see you later. Bye-bye.
Good night.
Bye.
Bye.